Hello everyone, very good evening to all of you. Good evening everyone, good evening. Good evening Mithun, Aniruddha, good evening. So, am I audible and visible? Audio and video both are clear. So, please type in a chat box. Video and audio both are clear. Okay, so shall we start today's session? Shall we start today's session? Shall we start today's session? So, beta, whatever we discussed in the previous class, right? Whatever the concept we discussed in the previous class, that is clear to everyone. Whatever we discussed in the previous class, that is clear to everyone. Whatever we discussed in the previous class, that is clear to everyone. So in last class, we discussed about effect of temperature on viscosity, right? In last class, we discussed about the effect of temperature. We discussed about effect of temperature on viscosity. Effect of temperature. Effect of temperature. Effect of temperature on viscosity of fluid. Right, in last class we discussed about effect of temperature on viscosity of fluid. Okay, now see here, just 1 minute. Okay, so if I'm talking about the liquids, in liquids, if I'm talking about the liquids, so as temperature increases, what happened with the liquid viscosity? As the temperature increases, what happened with the liquid viscosity? So as temperature increases, the liquid viscosity decreases. As temperature increases, the liquid viscosity decreases. Right? Good evening, Sahib. Good evening. And why it decreases? And why it decreases? Why it decreases? Why it decreases? Because cohesive force decreases. As temperature increases, cohesive force decreases. Right? We already discussed about the factors, right, which are responsible for the viscosity of the fluid. The first factor is a cohesive force, and the second factor is a molecular momentum exchange. And in liquids, if I'm talking about the liquids, in liquids that cohesive force is predominant or cohesive force is significant as compared to molecular momentum exchange. And we know that as temperature increases, as temperature increases, that intermolecular attraction force between the molecules decreases, right? And that's why the viscosity of the viscosity of the liquid decreases as the temperature increases. Right, now if I'm talking about the gases, so what happened in case of the gases? So in gases, as the temperature increases, that viscosity of gases increases. And why it increases? Because molecular momentum exchange increases. In gases, molecular momentum exchange is significant over the cohesive force. Okay, and in general, in general, in general, in general, in general, which having more viscosity, right, at a particular temperature. If I'm talking about at a particular temperature, in general, at a particular temperature, at a particular temperature, which having more viscosity, which having more viscosity, liquid having more viscosity or gases having more viscosity at a particular temperature, which having more viscosity at a particular temperature, liquid having more viscosity or gases? Tell me, at a particular temperature, which having more viscosity? Tell me. Yes, absolutely. Liquid having more viscosity at a particular temperature, liquid having more viscosity as compared to the gases, right? Liquid having more viscosity as compared to the gases at a particular temperature in general. Now, see this graph. Just 1 minute, just 1 minute, just 1 minute. Focus on this graph. Focus on this graph. Focus on this graph, beta. Right, focus on this graph. Basically, this is the graph between the absolute viscosity or viscosity versus temperature, right? Temperature versus viscosity. Temperature versus viscosity. So in a y-axis, viscosity, and in a x-axis, there is a temperature, right? In y-axis, there is a viscosity. In a y-axis, there is a viscosity. In a y-axis, there is a viscosity, and in x-axis, temperature. In x-axis, temperature. Now see, if I'm talking about the oils, if I'm talking about the liquids, see here. Focus on this graph, right? Castor oil, glycerine, SAE30 oil, right? This is a crude oil, right? Mercury, kerosene, right? So it is very much clear, as you increase the temperature, in case of the liquid, that viscosity decreases, right? From this graph, we can easily comment, beta. We can easily comment this graph. We can easily comment, as the temperature increases, that liquid viscosity decreases. It is very much clear, right? If I'm talking about the gases, right? If I'm talking about the gases, as the temperature increases, see here. If I'm talking about the gases, now focus here. Focus here. If I'm talking about the gases, now see, in case of the gases, these are the graphs, right? So in case of the gases, as the temperature increases, as temperature increases, the gases viscosity increases. And also it is very much clear at a particular temperature. If I'm talking about a particular temperature, so let us consider this particular temperature. Let us consider 80 degrees Celsius. Let us consider 80 degrees Celsius. Let us consider 80 degrees Celsius. So beta, liquid having more viscosity or gases having more viscosity? Liquid having more viscosity or gases having more viscosity at a particular temperature? At a particular temperature. So let us assume in this graph that is 80 degrees Celsius. So at a particular temperature, which having more viscosity? Liquid having more viscosity or gases having more viscosity? Yes, absolutely correct. Liquid having more viscosity. So at a particular temperature, liquid having more viscosity as compared to gases. right? So I hope you can understand these conclusion. I hope you can understand this. Okay, so basically this is the viscosity versus temperature plot, viscosity versus temperature plot, right? After that we discuss about some type of viscometer, right? Also we discuss about some type of viscometer, right? Also we discuss about some type of viscometer. So this is a problem based on the viscometer. We already discussed about the coaxial cylinder viscometer, right? Or simply concentric cylinder viscometer, capillary tube viscometer, 𝐂𝐤𝐻 viscometer, falling sphere viscometer. We already discussed, right? So in a list 1, type of viscometer is mentioned, and in list 2, the principle on which that viscometer works, that mentioned, right? So match the column, right? Match the column. Coaxial cylinder viscometer is based on which principle? Coaxial cylinder viscometer is based on which principle? Coaxial cylinder viscometer is based on which principle? So coaxial cylinder viscometer is based on the Newton's law of viscosity. Coaxial cylinder viscometer is based on the Newton's law of viscosity. What about the capillary tube viscometer? What about the capillary tube viscometer? What about the capillary tube viscometer? So I already discussed the capillary tube viscometer is based on the Hagen-Poiseuille equation. Capillary tube viscometer is based on the Hagen-Poiseuille equation. Now 𝐂𝐤𝐻 viscometer. 𝐂𝐤𝐻 viscometer. So 𝐂𝐤𝐻 viscometer is a efflux viscometer. 𝐂𝐤𝐻 viscometer is based on the efflux concept, right? So 𝐂𝐤𝐻 viscometer is a efflux viscometer. So C efflux viscometer, that is 4. And falling sphere viscometer is based on the Stokes law. Falling sphere viscometer is based on the Stokes law. So what is the correct match? What is the correct match? A, right? A3, B, right? B1, A3, B1, C4, D, C4, D, falling sphere, C4, D2, right? So this is the correct matching, right? A3, B1, C4, D2, A3, B1, A3, B1, A3, B1, A3, B1. So A is wrong, C is wrong, D is wrong, A3, B1, C4, D2. So correct answer is option B. Correct answer is option B. Fine. Okay, now come to the, okay, so tell me what is the effect of pressure on, viscosity? What is the effect of pressure on viscosity? Effect of pressure on viscosity. Effect of pressure on viscosity. Tell me effect of pressure on viscosity. That effect of pressure on viscosity. Effect of pressure on viscosity. So effect of pressure on viscosity, effect of pressure on viscosity of fluid is negligible. Right? Effect of pressure on viscosity of fluid is negligible. Right? So I hope you can understand this. Okay, now come to the next fluid property, which is a kinematic viscosity. Come to the next fluid property, which is a kinematic viscosity. Kinematic viscosity, or that is called momentum diffusivity. Kinematic viscosity, right? Kinematic viscosity or momentum diffusivity. So can anyone tell me what is a kinematic viscosity? What is a kinematic viscosity and why it is called momentum diffusivity? What is a kinematic viscosity? So beta, kinematic viscosity is denoted by a Greek letter which is nu. Right? Kinematic viscosity is defined by a Greek letter which is nu. And what is the kinematic viscosity? The kinematic viscosity is, it is ratio of It is ratio of dynamic viscosity. It is a ratio of dynamic viscosity to mass density, or simply you can say density. It is a ratio of dynamic viscosity to mass density, right? So that nu is equal to, that is a kinematic viscosity, and that is denoted by mu by rho. That mu by rho, that is nothing but the kinematic viscosity. Okay, now see here. Actually, beta, this why, see, we have already dynamic viscosity. Why kinematic viscosity is important? Or though we have the dynamic viscosity, why kinematic viscosity come into picture? Right? We already have the dynamic viscosity, right? That is a fluid property, right? So why there is need of a kinematic viscosity? Can anyone tell me? Can anyone tell me why there is a need of kinematic viscosity? Can anyone tell me? Beta, can anyone tell me? Though we have dynamic viscosity, though we have absolute viscosity concept, but why there is need of a kinematic viscosity? Can anyone tell me? Beta, actually this kinematic viscosity is the ratio of, right, is able to compensate the disturbances. Okay. See here. If I'm talking about the kinematic viscosity, beta, actually this kinematic viscosity is a ratio of two opposite property, right? Two opposite property of the fluid, right? How we can say, sir, two opposite property? Now see here, if I'm talking about the see, dynamic viscosity, if I'm talking about the dynamic viscosity, that kinematic viscosity is dynamic viscosity by density, right? So what it represent? If I'm talking about the dynamic viscosity, right? What dynamic viscosity represent? It represent the resistance in a flow, right? It represent resistance in a flow. Is it okay? It represent the resistance to flow. This property represent resistance to flow. Resistance to flow. Right? If dynamic viscosity is more, then definitely the resistance to flow is more. The second property, which is a density. Density is nothing but the measure of inertia or measure of heaviness. Actually, beta, this help to flow. Actually, this help to flow. That the numerator property of the fluid, resistance, offers resistance to flow. The numerator property offers resistance to flow, whereas the density offers, or density help to flow. So actually this kinematic viscosity is a ratio of two opposite property. The one property resist to flow, one property offers resistance to flow, and the another property help to flow. That's why this property come into picture. Right? Because there is some property, which is a ratio of two opposite property, or two, I can say, two opposite nature property. Right? And also, see, let us consider one layer. This is the one layer of a fluid, and this is the another layer. Let us consider this is the one layer of fluid, and this is the another layer. Now beta, let us consider this layer, or fluid particle present in this layer is flowing with a velocity of 10 meter per second. 10 meter per second. Right? This is the layer number 1. This is the another layer. Let us consider this is the layer number 2. This is the layer number 1. This is the layer number 2. So layer number 1 particle having velocity 10 meter per second. Right? So momentum transfer from layer 1 to layer 2. Then momentum transfer from layer 1 to layer 2 depends on mu and rho. Right? I hope you can understand this. The momentum transfer from layer 1 to layer 2. What will be the velocity of layer 2? What will be the velocity of layer 2, or what will be the velocity of particle present at the layer 2? That depends on the how much momentum is transferred by layer 1 to layer 2. Right? And this momentum transfer from layer 1 to layer 2, momentum transfer from layer 1 to layer 2, layer 1 to layer 2 is directly proportional to bonding between the molecules, or we can say it is directly proportional to cohesive force. It is directly proportional to cohesive force, or it is directly proportional to bonding between the molecules. So we can say it is directly proportional to cohesive force. We can say directly proportional to cohesive force, or we can say it is directly proportional to viscosity. Right? Whereas this momentum transfer from layer 1 to layer 2, that is directly proportional to 1 upon density, or we can say that is inversely proportional to density. If inertia is more, then momentum transfer will be less. Is it clear? So beta, can we say this momentum transfer, if you compile these two factors, then we can say that momentum transfer from layer 1 to layer 2 is directly proportional to mu by rho. Is it fine? So we can define, see, this is the fluid property. The dynamic viscosity is a fluid property. This density is a fluid property. That means the ratio is also a fluid property. Right? Dynamic viscosity is a fluid property. Density is a fluid property. So that means this ratio is a fluid property. And this ratio is called momentum diffusivity. Because momentum transfer from layer 1 to layer 2 depends on this too. Right? So that is called momentum diffusivity. Right? And also we can say this is the kinematic viscosity. So beta, it is clear why kinematic viscosity come into picture. Though we have the dynamic viscosity, but why kinematic viscosity come into picture? So actually the kinematic viscosity is a ratio of two opposite property, right, which tell us about the momentum transfer, or which tell us about the momentum diffusion from one layer to another layer. Right? That's why the dynamic viscosity is not sufficient to tell us how much momentum transfer from one layer to another layer. The dynamic viscosity does not tell us. Are you getting my point? So momentum transfer from layer 1 to layer 2 depends on the dynamic viscosity. It depends on the density, directly proportional to the viscosity, whereas inversely proportional to the density. That's why there is another property required which tell us how much momentum transfer from layer 1 to layer 2, and that's why the kinematic viscosity come into picture. Is it clear or not? It is crystal clear or not? These things you are not getting in any book, right? Whatever I explained, these things you are not getting in any book, but please try to understand these things. Is it clear? I want reply from everyone. Those students who are present here, I want reply from those students. Is it clear or not? Okay, fine. Now, come to the unit part. Right, come to the unit. Come to the unit. What is a unit? Come to the unit part, unit. So let's talk about the SI unit. Let's talk about the SI unit. Let's talk about the SI unit. So can anyone tell me what is the SI unit? Can anyone tell me what is the SI unit? Can anyone tell me what is the SI unit? What is the SI unit of the kinematic viscosity? What is the SI unit of the kinematic viscosity? Can anyone tell me? Okay, so it is simple, na? See, kinematic viscosity is mu by rho. Kinematic viscosity is mu by rho. And what is the unit of mu? So unit of mu is Newton second per meter square. Right? Into what is the unit of rho? That is kg per meter cube. That is kg per meter cube. And also we know that beta 1 Newton second per meter square is equal to 1 kg per meter second. We know na that 1 Newton second per meter square is equal to 1 kg per meter second. So we can write kg per meter second. Instead of Newton second per meter square, we can write kg per meter second into meter cube per kg. Right? So kg is cancel out, meter, and this is meter square. So ultimately what you are getting, meter square per second. So this is the SI unit of kinematic viscosity. Now if I am talking about the MKS unit, if I am talking about the MKS unit in MKS system, so in MKS system that unit is same, that is meter square per second. Right? If I am talking about the CGS system, if I am talking about the CGS system or CGS unit, so that CGS unit is centimeter square per second. That CGS unit is centimeter square per second. And this centimeter square per second is called, can anyone tell me what is this centimeter square per second? That is called Stoke. That is called Stoke. Right? So 1 Stoke is equal to 1 Stoke is equal to 1 centimeter square per second. Right? 1 Stoke is equal to 1 centimeter square per second. Right? Now, can you establish the relation between the SI unit and the CGS unit? Can you establish the relation between the SI unit and the CGS unit? So 1 Stoke is equal to 1 centimeter square per second, or we can say this is 10 to the power minus 4 meter square per second. So 1 Stoke is equal to, always remember, 1 Stoke is equal to 10 to the power minus 4 meter square per second. Right? So this is the relation between CGS unit. This is the relation between the CGS unit and the SI unit. Is it okay? Now see effect of temperature. Now see effect of temperature on effect of temperature on kinematic viscosity of fluid. Right? Effect of temperature on kinematic viscosity of fluid. Effect of temperature on kinematic viscosity of fluid. So what happened in case of the gas and what happened in case of the liquids? Right? In liquids, what happened? As you increase the temperature, then what happened? And in case of gas, what happened? In gases, right? In case of the liquids, when you increase the temperature, then what happened in case of the liquids? And when you increase the temperature, then what happened in case of the gases? Right? So effect of temperature on kinematic viscosity of fluid. Okay, so what happened in case of the liquid? What happened in case of the liquid? Can anyone tell me the answer? Or can anyone think about this? What happened in case of the liquid? What happened in case of the liquid? Okay, so see, if I'm talking about the liquids, if I'm talking about the liquids, we know now kinematic viscosity is the ratio of dynamic viscosity to density. Now, as you increase the temperature, as temperature increases, then what happened? As the temperature increases, then what happened with dynamic viscosity and what happened with the density as the temperature increases? I'm talking about the liquids now. So we know that as the temperature increases, the dynamic viscosity of liquid decreases. We know that as temperature increases, the dynamic viscosity decreases. Dynamic viscosity of liquid decreases. And also we know that as the temperature increases, the density, as the temperature increases, density decreases. As the temperature increases, density decreases. Right? Please try to understand this. As the temperature increases, if you increase the temperature, then dynamic viscosity of liquid decreases. Density of liquid decreases. So beta, if you see this expression, dynamic viscosity numerator also decreases and the denominator also decreases, right? But if you see this relation clearly, then you can understand this, that dynamic viscosity decreases more as compared to decrease in density. If you increase the temperature, then dynamic viscosity decreases more. Dynamic viscosity decreases more as compared to density. Sir, how you can say this? Sir, how you can say this? Sir? As temperature increases, dynamic viscosity decreases more as compared to decrease in density. So I will tell you example. So let us consider water, right? Let us consider water. So if you see here, beta, see, right? As the temperature increases, see, as the temperature increases, if you see here, as temperature increases, definitely that density, see, after 4 degrees Celsius, na? See, after 4 degrees Celsius, see, the density continuously decreases. So as the temperature increases, density decreases. Now come to the viscosity part. Now see here, that viscosity also decreases. But if you see this data, then it is very much clear that viscosity decreases more, right? For a given amount of temperature change, that decrease in or I can say for given amount of temperature change, it is very much clear that viscosity decreases more as compared to decrease in density. Is it fine now? And if you see this kinematic viscosity, see, this table is for the kinematic viscosity. So it is very much clear that kinematic viscosity decreases. So as the temperature increases, kinematic viscosity decreases in case of the liquid. Is it clear or not? Beta, is it clear or not? If I am talking about the liquids, in case of the liquid, as the temperature increases, the numerator value decreases more as compared to as compared to denominator value. And that is the reason as the temperature increases, that is the reason as temperature increases, that liquid kinematic viscosity decreases. Liquid kinematic viscosity decreases. Is it clear to everyone? Now come to the gases. What happened in case of the gases? What happened in case of the gases? What happened in case of the gases? So in case of the gases, as the temperature increases, in case of gases, as the temperature increases, then what happened with dynamic viscosity of gases? What happened with the dynamic viscosity of gases? So beta, as the temperature increases, the dynamic viscosity of gases increases. The dynamic viscosity of gases increases. And what about the density? What about the density? As the temperature increases, the density decreases. So it is very much clear. Numerator increases, denominator decreases. So ultimately what happened with the nu? The nu increases. So as the temperature increases, kinematic viscosity of gases increases. As the temperature increases, liquid kinematic viscosity decreases. Is it clear or not? Is it clear or not? Tell me, is it clear or not? Is it clear? Is it clear to everyone? Is it clear to everyone? No, gas also, why in gas also decreases? Sahib, in gas increases na beta, because numerator increases, denominator decreases. Right? So nu is directly proportional to mu. So mu increases, nu increases. Mu is inversely proportional to rho. So rho decreases, nu increases. So anyways, the nu increases. So in case of the gases, as temperature increases, the kinematic viscosity decreases. Okay. Now, can anyone tell me if you compare kinematic viscosity of liquid, can anyone tell me if you compare kinematic viscosity of liquid and kinematic viscosity of gases? Right? If you compare kinematic viscosity of liquid and kinematic viscosity of gases, so which one is the more? Kinematic viscosity of liquid is more as compared to kinematic viscosity of gases, or kinematic viscosity of gases is more as compared to the kinematic viscosity of the liquid, or both are possible? And whatever I am asking, that is corresponding to at a particular temperature. At a particular temperature. Right? What is your answer? At a particular temperature, what I am asking, at a particular temperature, tell me which one is the correct. Right? This is the option A, this is the option B. The liquid kinematic viscosity is lesser than the gas kinematic viscosity. Option C, both are possible. Option C, both are possible. And option D, none of this. So if you compare kinematic viscosity of liquid and the kinematic viscosity of gases at a particular temperature, then tell me which one is the correct. Which one is the correct? Okay, now see. Now see this graph, kinematic viscosity versus temperature. Now see this graph beta. See this graph, kinematic viscosity versus temperature. Kinematic viscosity versus temperature. So in a y-axis, kinematic viscosity, and in a x-axis, there is a temperature. Right? This is the temperature axis. This is the temperature axis, and this is the kinematic viscosity. Kinematic viscosity. Now, if I'm talking about a particular temperature, now let us consider at a particular temperature. So, at a particular temperature, okay, at a particular temperature, so let us consider that is 20 degrees Celsius. Let us consider 20 degrees Celsius. Let us consider 20 degrees Celsius. Let us consider 20 degrees Celsius. 20 degrees Celsius. 20 degrees Celsius. Let us consider 20 degrees Celsius. Now, at 20 degrees Celsius, if you see here, at 20 degrees Celsius, now see here, if I'm talking about the air and the oxygen, see here, air and the oxygen, air and the oxygen, air and the oxygen, see, right? This is the kinematic viscosity of air and oxygen, right? Now, if I'm talking about the crude oil is a liquid, na? Crude oil is a liquid. So, at 20 degrees Celsius, this is the kinematic viscosity of crude oil, right? At 20 degrees Celsius, kinematic viscosity of glycerin. So, glycerin liquid, air oxygen obviously gaseous, and see the crude oil is again liquid. So, tell me, at a particular temperature, beta, at a particular temperature, liquid kinematic viscosity is greater than the gas kinematic viscosity, or liquid kinematic viscosity is lesser than the gas kinematic viscosity. At a particular temperature, both are possible, right? Both are possible. We didn't specify which liquid, which gas. I'm normally asking, at a particular temperature, what happened with the liquid kinematic viscosity, and what happened with the at a particular temperature, what is the relation between kinematic viscosity of liquid and kinematic viscosity of gases. So I'm not specify the liquid and gases. So at a particular temperature, both are possible. The kinematic viscosity of liquid is greater than the kinematic viscosity of gas, or kinematic viscosity of liquid is greater than the kinematic viscosity of gas. So both are possible. Right. Now, at a particular temperature, now see here, at a particular temperature, right, kinematic viscosity of water and kinematic viscosity of air, right? At a particular temperature, what is the relation between kinematic viscosity of water to kinematic viscosity of air? Now see, again, if you see this graph, so kinematic viscosity variation with the temperature. Now see this graph. Right? This is graph for water. This is the graph for water. And this is the graph for air. Right? So at any temperature, not only at a particular temperature, at any temperature, right? At any temperature, we can say that water kinematic viscosity is lower than the air kinematic viscosity, right? So either you comparing at a particular temperature, or you are comparing at any temperature, or you are comparing or at any temperature, right? Kinematic viscosity graph of water is below the kinematic viscosity graph of air. So at any temperature, the kinematic viscosity of the water is lower than the kinematic viscosity of the air. Is it fine? So if someone asks you, what is the at a particular temperature, what is the relation between the kinematic viscosity of liquid and the kinematic viscosity of gas? So simply you can say, at a particular temperature, kinematic viscosity of the liquid more than the kinematic viscosity of gas, or kinematic viscosity of liquid is lesser than the kinematic viscosity of the gases. So both are possible. But if someone asks you, what is the relation between the kinematic viscosity of the water and the kinematic viscosity of the air? So simply you can say the kinematic viscosity of the water is lower than the kinematic viscosity of the air. Is it fine? Is it fine or not? Is it fine or not? Is it okay? Shall we proceed? Is it okay? Shall we proceed? Shall we proceed? Okay. Now come to the very important relation. Come to the very important relation between kinematic viscosity and temperature for ideal gases. Right? For ideal gases. For gases, and those gases are assumed as ideal gases. See here, relation between kinematic viscosity and temperature. Relation between kinematic viscosity and temperature for the gases, and that gases are assumed as an ideal gases. Okay, now see here, that nu is equal to mu by rho, right? That nu is equal to mu by rho. So if I'm talking about the dependency of mu with temperature, so what is the dependency of mu with temperature in case of the ideal gases? What is the relation between mu and temperature if I'm talking about the ideal gases? What is the relation? What is that relation? Beta, we already discussed, na? We already discussed in case of gases, the dynamic viscosity is directly proportional to the root over T. We discussed this part in the previous class. We discussed these things, right? Remember the Sutherland equation? Remember that Sutherland law? Remember the kinetic theory of gases, right? So we can say that dynamic viscosity of gases is directly proportional to root over T. What about the density? What about the density? So if you use the ideal gas equation, so we know that PV is equal to MRT. PV is equal to MRT, or simply we can say the P is equal to M by V RT. And what is the M by V? That is rho RT. So simply we can say that rho is equal to P upon RT. Right? Now, at a particular temperature, at a particular pressure, rho is a characteristic gas constant. So at a particular pressure, we can write now, at a particular pressure, we can write now density is directly proportional to 1 by temperature. Density is directly proportional to 1 by temperature. That we can write now at a particular pressure. Now see here, right? We know the relation of mu and T, and we know the relation between rho and T, right? So from here, we can say kinematic viscosity of gases, right? Kinematic viscosity of gases is directly proportional to root over T upon 1 by T, right? Root over T upon 1 by T. And from here we can say the kinematic viscosity of gases is directly proportional to, right? T1 by 2 plus 1. So 1 by 2 plus 1, that means it is 3 by 2. So this is very, very important relation, right? The kinematic viscosity of gases, which kind of gases? Ideal gases. The kinematic viscosity of ideal gases is directly proportional to T to the power 3 by 2, where T is the absolute temperature, na? Where T is absolute temperature. Absolute temperature means Kelvin scale, right? In Kelvin scale. In Kelvin scale. Right? The T is nothing but the absolute temperature. T is nothing but the absolute temperature. Right? So if we know kinematic viscosity corresponding to particular temperature T1, kinematic viscosity of gases, if we know the kinematic viscosity of gas corresponding to temperature T1, then we can easily comment on kinematic viscosity of gas at corresponding the temperature T2, right? Because we can say, write 𝜇1 by 𝜇2 is equal to, that is T1 by T2 to the power 3 by 2. Okay, is it clear or not? 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 Tell me. So if is it clear, then can we solve this MCQ problem? Can we solve this MCQ problem? This is the one MCQ problem. This is the one MCQ problem. So read the question carefully. First, read the question carefully. First, read the question carefully. In question, it is mentioned that kinematic viscosity of the air at 20 degrees Celsius is 1.6 into 10 to the power minus 5 meter square per second. Its kinematic viscosity at 70 degrees Celsius will be approximately. Right, so temperature increases, right? In case number 1, the temperature is 20 degrees Celsius. In case number 2, temperature increases to 70 degrees Celsius. Right, temperature increases to 70 degrees Celsius. So 20 degrees Celsius, that means it is 293 Kelvin. Right, 20 degrees Celsius, that means 293 Kelvin. And 70 degrees Celsius means it is 343 Kelvin. So temperature increases. And we know that as temperature increases, kinematic viscosity of gases increases. We know this part. As the temperature increases, the kinematic viscosity of gases increases. Now see, if you see these options, option B says it is same, 1.6 into 10 to the power minus 5. This is minus 5, na? Beta, this is minus 5, na? Minus 5. Right, option B says, if you increase the temperature, then kinematic viscosity remains same. So this is wrong. Kinematic viscosity increases. Option C says kinematic viscosity decreases. Option C says kinematic viscosity decreases. This is also wrong. The kinematic viscosity increases. Now come to the option A and option D. In option A, 2.2 into 10 to the power minus 5 meter square second, which is greater than 1.6 into 10 to the power minus 5. And option D says 3.2 into 10 to the power minus 5. Okay, so we know that relation, na? Air. In question, air is given. And we treat air as an ideal gas, na? We treat air as an ideal gas. So we know that relation. So we can write directly 𝜇1 by 𝜇2 is equal to, this is T1 by T2 to the power 3 by 2. Right, so 𝜇1 is 1.6 into 10 to the power minus 5 upon 𝜇2 is equal to T1. So what is the absolute temperature? T1, 20 degrees Celsius, right? Convert it into Kelvin scale. So 293. So 293 divided by, this is 343. 343 to the power 3 by 2. So calculate kinematic viscosity corresponding to 70 degrees Celsius. So what is the correct answer? Right, 2.2 into 10 to the power minus 5. No? 2.2 into 10 to the power minus 5 meter square per second. So this is the answer. This is the answer. Right, this is the answer. Okay, now come to the next question. Come to the next question. Come to the next question. Next question is MSQ question. Come to the next question. Next question is a MSQ question. Come to the next question. Next question is a MSQ question. No, Saturday you have class. Saturday you have class. Now see the next question. An incompressible fluid having kinematic viscosity 7.4 into 10 to the power minus 7 meter square per second and specific gravity 0.88 is held between two parallel plates. If the top plate is moved with a velocity of 0.5 meter per second, while the bottom one is held stationary, the fluid attains a linear velocity profile in the gap of 0.5 millimeter between these plates. Which of the following statement is correct? Right, so option A says shear stress experienced by top layer is 0.65 Pascal. Option B says shear stress experienced by the bottom layer is 0. Option C says shear stress distribution is uniform. And option D says maximum shear stress is 0.65 Pascal. So basically in this question, there are two plates. This is a plate number 1 and this is a plate number 2. Right? Bottom plate is fixed. Bottom plate is fixed, right? Bottom plate is fixed. And top plate is moving with some velocity. Top plate is moving with some velocity, which is mentioned in the problem. Right? Top plate is moving with some velocity, which is mentioned in a problem, top plate velocity. And that is equal to 0.5 meter per second. 0.5 meter per second. And in between these, in between two plates, there is a fluid having a specific gravity 0.88. So in between these two plates, there is a fluid having a specific gravity 0.88. Right? Having a specific gravity 0.88. Specific gravity 0.88. And also that gap is mentioned, no? Also this gap is mentioned. This gap between these two plates is 0.5 mm. 0.5 mm. Right? And also the velocity profile is mentioned. Right? Velocity profile for the fluid is mentioned, and that is the linear velocity profile. That velocity profile is linear. Velocity profile is linear. Right, so this is the velocity profile. That velocity profile is linear. Right, this is the velocity profile. Right, this is the velocity profile. Fine. And also in this problem, kinematic viscosity is mentioned. Kinematic viscosity is nu, and that is 7.4 into 10 to the power minus 7 meter square per second. Okay, now see, in this question, shear stress is asked. So to find out the shear stress, we have the Newton's law of viscosity, right? To calculate the shear stress in a layer, we have the Newton's law of viscosity. So use that Newton's law of viscosity. use that Newton's law of viscosity. So we know that from Newton's law of viscosity we can write, from Newton's law of viscosity, from Newton's law of viscosity, we can say shear stress experienced by any layer, right? Shear stress experienced by any layer, that is equal to mu du by dy at that layer, right? And see, this is your x-axis and this is your y-axis. So shear stress experienced by the any fluid layer is equal to mu du by dy. So first calculate mu, because kinematic viscosity is mentioned now. So we know that mu is equal to mu by rho, or simply we can say mu is equal to nu into rho, right? And in this problem that specific gravity is mentioned, and specific gravity is 0.88, that is equal to, so density of that fluid to density of water. So what is the density of this fluid? So simply we can write density of water, that is 1000 kg per meter, 1000 kg per meter cube. So it comes 880 kg per meter cube, right? The density of water is 1000 kg per meter cube. So 0.88 multiplied by 1000, so that comes 880 kg per meter cube, right? So we can write that mu is equal to, which is the dynamic viscosity, 7.4 into 10 to the power minus 7 multiplied by 880, right? And this is equal to, it comes in Pascal second. Pascal second. So can anyone tell me? So can anyone tell me what is the dynamic viscosity? So 7.4 into 880, 6512, right? 6512 into 10 to the power minus 7 Pascal second. So this is the dynamic viscosity, right? This is the dynamic viscosity. Fine. Now see here. Now see beta. In this problem, it is clearly mentioned that velocity profile is linear. In this problem, it is clearly mentioned. The velocity profile is linear. The velocity profile is linear. If this is the bottom plate, this is the top plate which is moving with a velocity of Vt, it is clearly mentioned in this problem the velocity profile is linear, right? This is the velocity profile. This is the velocity profile. So if velocity profile is linear, so simply we can write, if velocity profile is linear, then simply we can write now that du by dy is equal to delta u by delta y. We can write now, if velocity profile is linear, then du by dy is equal to delta u by delta y, right? So if you calculate the slope, what is the speciality of the straight line? If you calculate the slope here, the slope is same, right? So if velocity profile is linear, then directly we can write this du by dy is equal to delta u by delta y, right? Or we can say this is also equal to, we can write the top plate velocity minus bottom plate velocity divided by gap between these two plates. This we can write in case of the linear velocity profile only. This we can write in case of the linear velocity profile only. Is it clear now? So directly we can write that tau at any y is equal to, this is mu into, right? Since velocity profile is linear, u top minus u bottom divided by gap between these two plates, right? Now that shear stress, now see here, Now see here, the shear stress experienced by the any layer, because in this case now this du by dy is constant. In this case beta du by dy is constant. Let us consider, if you are in this question it is clearly mentioned the velocity profile linearly varies now. So let us consider the velocity profile as a plus by. This is the linear variation, right? Velocity profile varies linearly. So let us consider, right, velocity variation with respect to y. So u is equal to a plus by, where a and b are constant, where a and b are constant, where a and b are constant. So beta, if you calculate du by dy, if you calculate du by dy, then it becomes b na. If you calculate du by dy, then it becomes b na. That means your du by dy is not function of, your du by dy is not function of y in case of the linear velocity profile. The du by dy is not function of y in case of the linear velocity profile. So beta, now see here, this, if you see this Newton's law of viscosity, mu is not function of y. The mu is constant, mu each layer having same viscosity. So mu is independent of y. This du by dy is independent of y for the linear velocity profile. That means each layer experiences the same shear stress, right? When velocity profile is linear, then du by dy is not function of y, right? So we can write tau is also not function of y. Tau is also not function of y. That means each layer experiences the same shear stress. Are you getting my point? And how you calculate the shear stress? You can easily calculate the shear stress from here, right? In case of the linear velocity profile, directly we can write this, right? Now see, mu we already calculated 6512 into 10 to the power minus 7 into, what is the top plate velocity? The top plate velocity is 0.5. Bottom plate velocity, that is 0, divided by, what is the gap? The gap is 5 mm, 0.5 mm. So 0.5 mm, that means 0.5 into 10 to the power minus 3 meter. Right. So calculate tau at any y. So this comes 0.5 cancel out, 10 to the power minus 3, and this 10 to the power minus 4, and this comes 0.6512 Pascal. So this is the shear stress. So beta, each layer experiences the same shear stress. Is it clear to everyone? So if you draw the shear stress variation, beta, if you draw the shear stress variation, see, if you draw the shear stress variation, this is the shear stress variation. See, this is the shear stress variation, right? So here, this is the velocity variation, and this is the tau variation. So each layer experiences the same shear stress, right? So shear stress experienced by the top layer is 0.65 Pascal. Yes, shear stress experienced by the top layer is 0.65 Pascal. Absolutely correct. Shear stress experienced by the bottom layer is 0. No, beta, shear stress, we know that at the bottom layer, we know that shear stress is maximum, right? Since that profile is linear, since the velocity profile is linear, so each layer experiences the same shear stress. So bottom layer, top layer, any layer experiences the same shear stress. So shear stress experienced by the bottom layer is 0. No, this is absolutely wrong. Now come to the statement number D. Shear stress distribution is uniform. Is it correct or not? Shear stress distribution is uniform. Correct or not? Yes, your shear stress distribution is uniform. So C is correct. Shear stress distribution is uniform. C is correct. Now come to the statement D. That statement D says maximum shear stress is 0.65 Pascal. Yes, maximum shear stress is also 0.65 Pascal. So what is the correct answer for this question? Correct answer for this question is A. A is correct, C is correct, and D is correct. A is correct, C is correct, and D is correct. Is it clear to everyone? This question is clear or not? This is clear or not? Beta, uniform na? Shear stress distribution is uniform na? This is linear or uniform? This is linear or uniform? Tell me. This is linear or uniform? Beta, uniform na? Okay, so is it clear to everyone? Is it clear to everyone? So shall we move the next part? Shall we move to the next part? Now come to the next part. So next part is application of the Newton's law of viscosity. Right, next part is the application of Newton's law of viscosity. So we discuss about the Newton's law of viscosity in very detailed manner. Now come to the application of Newton's law of viscosity. So the first application, bottom plate is fixed and the top plate is moving with constant velocity, that is V. Right, we already discussed this case in the previous question only. Right, the bottom plate is fixed. So let us consider, see, this is the top plate, right? This is the top plate and this is the bottom plate. Right, this is the bottom plate and this is the top plate. And this is the bottom. This is the bottom plate. So in this case, we assume bottom plate is fixed, whereas the top plate is moving with certain velocity, with certain constant velocity na, so that constant velocity is V. So let us consider that is Vt. Vt is equal to V. Right, so top plate is moving with the constant velocity, that is V. And in between these two plates there is a fluid, right? And see here, what we assume in the fluid, that velocity profile is linear. So beta, this is our assumption. This is our assumption. Velocity profile. This is our assumption. Velocity profile is linear. This is our assumption. The velocity profile is linear. This is our assumption. Please try to understand this. Velocity profile is linear. Maybe in future you are getting a cases where velocity profile is non-linear. But here what I'm assuming here, velocity profile is linear. So velocity profile, the fluid layer attains linear velocity profile. So this is the velocity profile. This is the velocity profile. Right, this is the velocity profile. U is function of y, and U linearly varies with y. Now, if we want to calculate the shear stress, we already calculate the shear stress in the previous problem. But now see this case in a very in a detailed manner, right? So if I'm talking about the velocity profile, so let us consider this velocity profile is linear. We assume this velocity profile is linear. So let us consider velocity profile varies like this. U is equal to a plus by. Let us consider the velocity profile vary like this. U is equal to a plus by, where a and b are constant. Where a and b are constant. Where a and b are constant. Now beta, can you tell me the exact velocity profile? Can you find the value of a and b? Can you find the value of a and b? Can you find the value of a and b? So to find the value of a and b, to find out the value of a and b, there is a need of boundary conditions, right? To calculate the value of a and b, there is a need of boundary condition. There is need of a boundary condition. So let us just 1 minute now. Let us consider this gap is h. This is the x direction and this is the y direction. Okay. So to calculate a and b, there is a need of boundary condition. So can anyone tell me what is the boundary condition? What are the boundary condition? Obviously, two boundary conditions are required. Obviously, two boundary conditions are required. Two boundary conditions are required. Right? There are two constants, so two boundary conditions are required. So can anyone tell me what are the boundary conditions? So beta, it is simple now. Boundary conditions. If I'm talking about the boundary conditions, so at y is equal to 0, that u is equal to 0, no slip condition. At y is equal to 0, u is equal to 0 because bottom plate is stationary. And also we can write at y is equal to h. At y is equal to h, that u is equal to Vt. U is equal to Vt. Right? These are the no slip condition. One no slip condition at y is equal to 0, another no slip condition at y is equal to h. So we can write in this way. Now we have two boundary conditions. Now find out the value of a and b. So if we use the first boundary condition, so at y is equal to 0, u is equal to 0. At y is equal to 0, u is equal to 0. So from first boundary condition, that a becomes 0. When you apply the first boundary condition, that a becomes 0. At y is equal to 0, u is equal to 0. So a becomes 0. And if you apply the second boundary condition, then at y is equal to h, u is equal to Vt. Right? Vt is equal to a0 plus b into that is h. So b is equal to, we can write Vt by h. Right? That b is equal to Vt by h. Right? Now put the value of a and b. Now you are find the exact velocity profile, that u is equal to a value is 0 and b value is Vt by h. Vt by h into y. Right? So this is the velocity profile. This is the velocity profile that u is equal to Vt by h into y. Is it clear to everyone? Okay. Now I want to find out the shear stress. My main focus is on shear stress. So we know that Newton's law of viscosity. We know that Newton's law of viscosity. So as per the Newton's law of viscosity, we can write that shear stress at any y is equal to mu du by dy at that y. Right? So if you calculate du by dy, calculate du by dy from here. Calculate du by dy from here. So if you calculate du by dy from here, then it is very much clear. It become Vt by h. It is Vt by h. where Vt by h is constant. That means beta your du by dy is not function of y. The du by dy is not function of y because velocity profile is linear. So we can directly write this du by dy is equal to, so tau at any y is equal to, this is mu into this is Vt by h, mu into Vt by h, mu into Vt by h. So this is the shear stress experienced by any layer, and it is also very much clear in this expression there is no y na. That means shear stress is not function of y. Shear stress is not function of y. That means each layer experiences the same shear stress. Each layer experiences the same shear stress. Each layer experiences the same shear stress. So if you draw the shear stress variation, so this is the shear stress variation. This is the shear stress variation. The shear stress variation is uniform. The shear stress variation is uniform. Right? This is the velocity variation. Right? This is the velocity variation. This is the velocity variation. And this is the shear stress variation. This is the shear stress variation. This is the tau variation. This is the tau variation. Is it clear? Right? And if you want to generalize this expression, right? If you want to generalize this expression for the linear velocity profile, right? Might be in future you are getting some problem in which this bottom plate is not fixed, right? In future you are getting a problem in which bottom plate is not fixed. Bottom plate is also moving with some velocity. So if you want to generalize this expression, so we can write in this way, right? This is very simple. Beta. For linear velocity profile, there is no need to calculate the value of A, there is no need to calculate the value of B if velocity profile is linear. If velocity profile is linear, then there is no need to calculate the value of A and calculation of value of B. If the velocity profile is non-linear, let us consider some u is equal to a plus by plus cy square like this, right? Parabolic velocity profile, second degree parabolic velocity profile. On that case, definitely there is need of calculation of a, b and c, right? But in this case, when the velocity profile is linear, there is no need to calculate this a and b. No need to calculate a and b. You can directly write for linear velocity profile, right? You can directly write du by dy is equal to delta u by delta y, or simply you can write top velocity minus bottom velocity divided by gap. Top velocity minus bottom velocity divided by gap, or simply we can write the tau at any y is equal to mu into, this is top velocity minus bottom velocity divided by gap. Right? In general, we can write in general. Is it clear to everyone? Is it clear to everyone? Okay, so this is the funda behind the calculation of the shear stress. If someone asks you what is the shear stress at the bottom, the shear stress at the bottom is maximum, right? In this particular case, each layer experiences the same shear stress. Actually, what is the reason that most of the students confuse at the y is equal to 0, the shear stress is 0, right? Most of the students may confuse here. At y is equal to 0, if I ask you in general, even in interviews also, if I ask at y is equal to 0, what is the shear stress? So most of the students says at y is equal to 0, the shear stress is 0. Beta, y is equal to 0, shear stress is not 0. Even at y is equal to 0, the shear stress is maximum at the surface. right? At the surface, the shear stress is maximum. So there is one reason actually. At y is equal to 0, u is equal to 0. At y is equal to 0, u is equal to 0. Why u is equal to 0? Because bottom plate is stationary. So at y is equal to 0, u is equal to 0. So we think that du by dy is equal to 0. Beta, actually this du by dy, na, this is du by dy, this du in this expression, this du. Please try to understand this. Du, actually du is the relative velocity, but beta du is not relative velocity between the plate and the fluid layer. Please try to understand this point. Here, if you see this du, beta, actually this du is not relative velocity between the plate and the fluid layer. Actually, most of the students think this du is the relative velocity between the plate and the fluid layer. Are you understand my point? The most of the student think this du is the relative velocity between the plate and the fluid layer, but beta, actually this is the relative velocity between the fluid layers. This is the relative velocity between the fluid layers. Are you understand my point? Are you getting this point or not? Are you understand this point or not? The most of the student think, sir, at y is equal to 0, that u is equal to fluid layer velocity is equal to plate velocity. That's fine, that's correct. There is no problem with this. There is no problem with this. At y is equal to 0, the fluid layer velocity is equal to plate velocity. There is no problem with this. Right? Or we can say at y is equal to 0, no relative velocity between plate and the fluid layer. But when you see this Newton's law of viscosity, in this Newton's law of viscosity, that du, beta, that is the relative velocity between the fluid layers. That is the relative velocity between the fluid layers which are dy distance apart. Please try to understand this point. This is a very, very basic point. The most of the students may confuse here. Are you getting my point? Beta, if you write this is the Newton's law of viscosity. This Newton's law of viscosity for the fluid layers. This is the Newton's law of viscosity. This Newton's law of viscosity is for the fluid layer. So here, the du by dy, the du is the relative velocity between the fluid layers which are dy distance apart. So at the plate, right? Or I can say at y is equal to 0. At y is equal to 0. At y is equal to 0, this du by dy is maximum. Okay, fine. This is the non-linear, sorry, this is the linear case. In this linear case, every layer having same du by dy, because this is a linear velocity profile. Every layer having same du by dy. That's why you are getting each layer, at each layer you are getting the same shear stress. But if the profile is non-linear, if u is equal to a plus by plus cy square like this, then beta, at y is equal to 0, the maximum du by dy, at y is equal to 0, the du by dy is maximum. And that's why at y is equal to 0, you are getting maximum shear stress. So whatever the concept, okay, theoretically also I will try to I try to explain theoretically also and experimentally also. Obviously, at the surface, the shear stress is maximum. There is no doubt on this. Is it clear or not? Tell me, guys. This is a very fundamental thing. Is it clear or not? So don't confuse in, don't make mistake in future, na? Don't make mistake in future. Don't make mistake in future. Okay, now what is the power required, right? See, this plate moving with some constant velocity, right? This plate is moving with some constant velocity. But we know that beta in this plate shear stress act na, right? In this plate shear stress act na, and because of that shear stress, that shear stress try to reduce the velocity. Getting my point? So what is the power required? If I ask you what is the power required, what is the power required? If I ask you power required, power required to maintain, what is the power required for top plate, power required for top plate to maintain constant velocity, or simply we can say what is the power required to overcome the friction. What is the power required to overcome the friction? Power required to overcome the friction. What is the power required to overcome the friction? So what is the power required to overcome the friction? Simply, this is the shear force experienced by the top plate. That is the shear stress experienced by the top plate multiplied by velocity of the top plate. Multiplied by the velocity of the top plate. Shear stress experienced by the top plate to velocity of the top plate. So from here, you are getting the power required to overcome the friction. Right, and what is the shear stress at the top plate? What is the shear stress at the top plate? So simply tau is equal to F, tau is equal to Fs by A na, Fs by A. So Fs is equal to, that is tau multiplied by A, right? A is the area of plate which is in contact with the fluid. Area of plate contact with fluid. Right, so from here you can easily find out the power required to overcome the friction. Is it clear or not? Is it clear? And shear stress distribution is uniform. In this case, the shear stress distribution is uniform. Also, this is very, very important point. If velocity profile is linear, this is also very, very important point. If velocity profile is linear, then shear stress is not function of y. That means shear stress distribution is uniform. That means shear stress distribution with y is uniform. That means shear stress distribution with y is uniform. Fine. Now, see. Now come to the subcase of case number 1. Subcase of case number 1. Right, subcase of case number 1. Right, number of subcases are possible, beta. Number of subcases of case 1 is possible. Let us consider. See, this is the top plate. This is the bottom plate. Right? Top plate is moving with velocity. Top plate is moving with velocity Vt. Right? Or you can say Ut. Right? Top plate is moving with some velocity. Let us consider that is Ut. And bottom plate is moving with velocity, that is Ub. But opposite direction. Right? direction is opposite, and in between there is a fluid. In between there is a fluid. In between there is a fluid. Right? And let us consider ut is greater than ub. Let us consider that ut is greater than ub. Let us consider that ut is greater than ub. Right? So this is the top plate. Top plate is moving with a velocity of ut in a positive x direction, and bottom plate is moving with a velocity of ub in a negative x direction. And what I am assuming here, let us consider ut is greater than ub. Let us consider. Now again I am assuming here also the velocity profile is linear. Right? Again I am assuming here velocity profile is linear. Velocity profile is linear. So in most of the problem, if velocity profile is not mentioned, right? If you are getting a problem in which velocity profile is not mentioned, then assume that velocity profile is linear. Right? This is the only way to solve the problem. Right? If velocity profile is mentioned, then take that velocity profile. But if velocity profile is not mentioned in a problem, then assume that velocity profile is a linear velocity profile. This is the only way to solve the problem. Right? So here I am assuming velocity profile is linear. Here I am assuming that velocity profile is linear. Okay. Now see, this is the velocity profile. This is the velocity profile. This is the velocity profile. Right? This is the velocity profile. Right? And also I am assuming this gap, right? Gap between the top plate and the bottom plate, that is h. Okay. So can you find out the shear stress in this case? Can you find out the shear stress? Okay, first tell me what is the shear stress distribution. First tell me what is the shear stress distribution. First tell me what is the shear stress distribution. The shear stress depends on the y. Because shear stress depends on the y. What is the shear stress distribution? Tell me what is the shear stress distribution. What is the shear stress distribution? The shear stress distribution is uniform. That shear stress distribution is uniform. That shear stress distribution is uniform, beta. I already clearly written here, na? If velocity profile is linear, then the shear stress distribution is uniform. So what is the shear stress distribution? The shear stress distribution is uniform only. This is the shear stress distribution. This is the shear stress distribution. Right? This is the tau variation. This is the tau variation, right? And this is the u variation, velocity variation, and this is the tau variation. Okay, better now calculate. If you want to find out the shear stress, if you want to find out the shear stress, then use the Newton's law of viscosity. That is the only tool that you have. This is the only tool that you have. Newton's law of viscosity. Newton's law of viscosity. And we know that as per the Newton's law of viscosity, that tau at any y is equal to, this is mu du by dy at that y. Tau at any y is equal to mu du by dy at that y. Fine. Now, velocity profile is linear, na? So directly we can write. Directly we can write that is mu multiplied by, what is the du? That is the top velocity minus bottom velocity divided by gap. No problem. Velocity profile is linear. We can directly write u top minus u bottom divided by gap. Is it fine? Now see that mu is equal to mu into, sorry, tau at any y is equal to mu. Now u top minus. Now use proper sign convention now. Use proper sign convention, beta. Use proper sign convention. Proper sign convention means, sir, see, top plate is moving in the positive x direction. Bottom plate is moving in the negative x direction. So minus ub, right? Minus ub divided by, what is the gap? That gap is h. So simply we can write this is the mu multiplied by ut plus UB divided by gap divided by H. So this is the shear stress experienced by the any layer. This is the shear stress experienced by the any layer. Is it fine? You can easily calculate. If let us consider I am giving some value. Let us consider I am giving this fluid viscosity as a 2 poise. Right, I am giving top velocity as a 10 meter per second. I am giving the bottom velocity as a 5 meter per second. So can you calculate the shear stress? Can you calculate the shear stress? Yes, sir, we can calculate the shear stress. Can you find out the shear stress distribution? Yes, we can find out the shear stress distribution because velocity profile is linear, therefore shear stress distribution is uniform. Each layer experiences the same shear stress. Each layer experiences the same shear stress. Is it clear? Is it clear? Okay, fine. Now beta, if I ask you, can you find out the distance from the bottom plate? Can you find out the distance from the bottom plate where velocity is 0? Can you find out the distance from the bottom plate where the velocity is 0? Where the velocity is 0? Can you find out the distance from the bottom plate where the velocity is 0? Right, again, this is the x-axis, this is the y-axis. At y is equal to 0, that u is equal to ub. Or you can say at y is equal to 0, u is equal to minus ub. At y is equal to plus h, or y is equal to h, u is equal to ut. So if I ask you one question, can you find out the distance from the bottom plate where the velocity is 0? Let us consider that is a. Let us consider that is a. So at y is equal to a, at y is equal to a, the fluid layer velocity is 0. This layer, right, this layer at y is equal to a, this layer having 0 velocity, this layer having 0 velocity, because beta velocity changes from minus 5 to plus 10. Now let us consider the bottom plate velocity is 5 meter per second and the top plate velocity is 10 meter per second. So your velocity changes between minus 5 meter per second to 10 meter per second. Na beta, your velocity changes minus 5 meter per second to plus 10 meter per second. Na? So in between, if you change, if you go minus 5 to plus 10, so definitely there is a some point where velocity is 0. The bottom layer having velocity minus 5 meter per second, top plate having velocity plus 10 meter per second. So in between there is a layer having velocity 0. So can you find out that layer having velocity 0? Yes, we can find out. So simply let us consider at a distance from the bottom plate the velocity is 0. If this is the a beta, so obviously this is h minus a. Obviously this is h minus a, and this is equal to ut. This is equal to ub. So if you apply the similar triangle, right, from the similar triangle concept, from similar triangle concept, from similar triangle concept, we can say na, from similar triangle constant ut upon h minus a or h minus a upon ut is equal to, right, h minus a upon ut upon a by ub, upon a by ub. So simply we can write this is h minus a divided by a is equal to, this is ut by ub, right, and simply we can write h by a minus 1 is equal to ut by, that is ub. Now you can write h by a is equal to 1 plus ut by ub, right, or h is or a is equal to h upon 1 plus ut by ub, right. So this is the a, this is the a, right. So you can easily calculate the distance from the bottom plate where velocity is 0, distance from the bottom plate where velocity is 0. Is it clear? Okay. So I think this is sufficient for today's class. We will discuss remaining topics related to the Newton's law of viscosity in the next class. Right. So today we covered kinematic viscosity. Today we covered effect of temperature on kinematic viscosity. Effect of temperature on kinematic viscosity. Also we discussed why kinematic viscosity is called momentum diffusivity. Also we discussed some problems and application of Newton's law of viscosity. So application of Newton's law of viscosity is not completed now. Application of Newton's law of viscosity. Right? So there are a number of cases. That cases we will discuss in next class. So beta, I hope whatever we discuss in today's class, that is clear to everyone. Okay. So thank you so much. Any doubt? Anyone having any doubt? Anyone having any doubt? Okay, no doubt. Okay. So thank you so much. Bye bye. Take care and good night, everyone. Good night.